Interpolation procedures depend on the characteristic of X intervals. In this video, we showcase methods when dataset has regular X intervals. Welcome to Numerical Solutions to CE Problems. Given a set of 5 data points, note the X interval where in this case we have an interval h as 1. In both procedures that we will discuss, a difference table is necessary. Then we employ a method corresponding to the required. Start off with Newton's difference table. The first two columns would consist of x and f of x. The next column will be tagged as delta y as we are to take the difference of the y's. That would be started by 4.28 minus 3, which is 1.28. The next is 5.88 less 4.28, resulting to 1.6. Next is 7.8 minus 5.88, giving 1.92. Then last in the column is 10.04 minus 7.8, which is 2.24. Since it is too early for the values to converge, we continue with the next difference, which we label as delta square y. We start with 1.6 minus 1.28, which is equal to 0.32. Next is 1.92 minus 1.6, which is 0.32 again. Then the last difference is with 2.24 and 1.92, also yielding 0.32. Note that values at this column are already constant, so we can stop from here on. However, let's continue filling up the table until convergence. For delta cube y, the first value is 0.32 less 0.32, which is 0. Then the same follows for the next difference, making both values in this column 0. Also, the fourth column will still yield 0. Having filled the table, we check locations of the tasks. We are to determine f of 2.8, which is somehow at the first half of the set. The next is f of 5.4, which can be situated at the rear end of the dataset. In order to identify the method to be used, mark the mid-value of the set, that is at 5.88. Now it is clear that 2.8 is before the mid-value, so we are to use forward interpolation, and this would mean that coefficients to be used later are from the leading forward differences. 5.4 on the other hand falls within the second half, so the coefficients to be used in the formula later are those from the leading backward differences. Now let's focus on solving for f of 2.8. We have identified that to solve this, we are to use Gregory-Newton's forward interpolation, the formula of which is the one written. F of x is equal to the reference y plus r times delta y plus the next term which comprises of r with r less 1 times delta squared y all upon 2 factorial. You would notice that the next term is just an iteration with additional r minus 2 all over 3 factorial. Then the terms multiplied by delta cube y. The next thing to do is to identify the individual parameters. Y0 is the reference y value. This is the value of y closest to the y we are looking for. By closest, we meant the closest y before the unknown f of x. In the example, the closest y before the unknown is 3. The next parameter to compute is r. R or some use k, p, or any variable, is solved as the required x less the reference x all over the x interval. This is denoted as x minus x naught all over h. In the example, we have r as 2.8 minus 2 upon 1, giving 0.8. Next are the deltas from the difference table. We take 1.28 for delta y. 0.32 is for delta squared y. Then 0 for delta cubed and delta raised to 4y. Having all parameters for the equation, we work on f of 2.8 as y naught, which is 3, plus 0.8 for r times first delta as 1.28. Then the next term is 0.8 multiplied by 0.8 less 1 upon 2 factorial times delta squared, which is 0.32. If we still write and complete the other two terms to convergence, we have the next as 0.8 times 0.8 less 1, then 0.8 less 2 upon 3 factorial, then this is multiplied by the delta, which is 0. The last term follows the same procedure, showing 0.8 times 0.8 less 1 times 0.8 less 2 and 0.8 less 3 over 4 factorial. Delta for the fourth term is also 0. Simplify all terms and have 3 plus 1.024 plus negative 0.0256 plus zeros, and have f of 2.8 as 3.9984. This value is within the range of 3 and 4.8. How about for f of 5.4? Since this is way back to the rear of the dataset, we will be using Gregory-Newton backward interpolation. The formula for this approach is y sub n plus r times nebula y plus the next term comprising of r with r plus 1 and nebula y squared y upon 2 factorial and so on. Next is to dissect each parameter. Y sub n is the reference y, which is the closest y after the required y. In this example, the nearest y to the unknown is 10.04. R is taken this time as the required x less the reference x all over the x interval. This is written as x minus x sub n over h. This is 5.4 minus 6 over 1, giving negative 0.6. For the nebulas, we use 2.24 as nebula y, 0.32 for nebula squared y, and both nebula cubed and nebula raised to 4 use 0. Having all parameters identified, plug them into the equation, so f of 5.4 is y sub n of 10.04 plus negative 0.6 times nebula of 2.24. The next term has negative 0.6 times negative 0.6 less 1 over 2 factorial, then this is multiplied by 0.32. The procedure goes on although the third and the fourth terms are multiplied by 0, disregarding them. Thus, f of 5.4 is 10.04 plus negative 1.344 plus another negative 0.0384, which is then taken as 8.6576. This value is within 7.8 and 10.04.